One of the hardest things about developing blockchain programs is making sure that they are correct. I mean, really, this is one of the things that's hard about programming in general, but in most domains, it doesn't really matter. So, for instance, when you are using photo editing software, yeah, it's not good that it breaks and like crashes or something like that, and you can lose your work. And, it's important to have programs like that not fail. But it's even more important to have something like a cryptographic protocol or, bank software not fail because there can be, large monetary consequences for doing something like that wrong. Similarly, of course, you wouldn't want the software controlling a pacemaker or, a vehicle to fail because people's lives are at stake with that. Now, the thing is that with blockchain programs, essentially every program is one of these high assurance pieces of software because the main thing that decentralized applications do is they deal automatically with funds of some sort, whether that's the network token of, like Ethereum or Algorand, Algos, etc., or whether they deal with some other kind of token that is custom to that application. So, a a side token, a liquidity token, things like that. Now, because they all deal with this, that means that they all are fund handling programs. And as fund handling programs, the program itself has complete authority over the what happens with those funds. So if you make an error programming it, then what that means is that your program will automatically say yes to requests to extract money, or will automatically say no when you meant to say no. And so that's why it's important for every one of these programs to be right. And we're all familiar with examples of blockchain programs having such errors and people losing lots and lots of money. So that's one of the main challenges of blockchain programming. And one of the things that Reach does is that every time you write a program, it automatically takes that program and turns it into a system of equations where if that system of equations has a solution, then your program has an error in it. I'm going to share my screen for a little bit. And what I have loaded up here is a little terminal window for editing code, reference to our documentation. And now I'm looking at the section 2.5 of the tutorial about trust and commitments. In this step of the tutorial, we talk about how to identify problems with an implementation of rock, paper, scissors. So if we go down to one of the examples, we talk about how, when you have an implementation of a program like rock, paper, scissors, we have a simple computation that we intend to be the way to calculate who the winner is. Now, of course, this program doesn't really have anything to do with, blockchain program or anything like that. It's an obvious program, but it's an obvious program that we hope we'll be able to get correct. And so we can write this program, and then what Reach allows us to do is we can add assertions to the code, like I'm going to assert that when we call this function winner with rock and paper, then Bob wins, but if we call it with paper and rock, then Alice wins. Now, these assertions, they essentially are like test cases, like you would write in a, quote, normal programming language. You give concrete inputs, and you write down what you expect the output to be, and Reach will tell you if there's an error. However, we can write even more expressive statements about what our program is supposed to do by using forms like for all. So what for all does is it's going to say, consider all possible unsigned integers for hand, and consider all possible unsigned integers for hand B. And then let's make sure that the result of calling winner is one of the valid outcomes. Or maybe we could look at an example like for all unsigned integers, hand, if I send hand in on both sides of a game of rock, paper, scissors, I expect to get back a draw. Now, you might think that if you were to try to implement this yourself, then the way to do that would be to enumerate all 2 to the 256 possibilities for that number and actually run the program. Now, you could do that, and that would be a way of checking it. But that's not what Reach does. Instead, what Reach does is it builds a system of equations. And what I want to do is kind of go behind the scenes a little bit and show like actually how that works to kind of demystify it a little bit. So what I have right here on the right-hand side is a program written in the Theorem Perverse that we use. It's called Z3. So we're going to just do a really simple example. So imagine that we have a variable x, which is an integer, and a variable y, which is an integer. So this extremely verbose way of writing I've just declared these two variables, x and y. So the Z3 is just a programming language. Now what I can do is I can write down a system of equations. And the way that we write down a system of equations is by writing assert. This asserts a fact. So I'm going to write down the fact that x is equal to 3. Then I'm going to write down the fact that y is equal to x. So this right here is a system of equations, and you are smart. So you know what the solution is. The solution is that x is 3 and y is 3. And we can actually write down, we can tell the Z3 theorem prover that we would like to know that by writing get model. Now when we run this, it says model's not available. We have to write check satisfiability. And then it says, aha, yes, that is satisfiable. Satisfiability is code for there is a solution to the system of equations. And here we say that y is 3 and x is 3. Now, sometimes we can write something that is slightly more complicated. Maybe we'll say that x is equal to y plus 1. Now, again, you are smart and you know that now this means that y is equal to 2. Now, if you were doing this on paper, you would be able to say, aha, I'll substitute 3 into x, then I'll subtract 1 from both sides, and I'll get with y equals 2. So the kind of things that you did when you were in, middle school or high school solving system of equations, Z3 does for us. Now, the thing that's interesting about Z3 is that it allows us to write down more interesting properties because we can make quite complicated sets of equations. So let's look at an example of this program right here, where we have winner is equal to hand is a function that takes hand A and hand B, and we have hand A plus 4 minus hand B percent 3. So let's write this particular theorem that we saw down there. So what we're going to do is we're going to take the theorem that winner hand equals draw. That's what we're going to look at. Okay, so what is winner? We'll say declare function winner. Okay, and what we want to know is we want to assert that it is the case that the winner is equal to draw. Draw is the first one, so that means it's the number 1. Okay, so we're going to assert that it's equal to winner, so that winner is equal to 1, where winner is equal to, what is it? The hand plus 4 minus the hand percent 3. Now, we have to rewrite this so that it's in prefix notation. And then we'll put the percent right here. Okay, and so what I've just done is I've asserted that there is something called a hand. I don't know what it is, though. There's something called winner, and winner is equal to this computation. And now I'm going to assert whether or not the winner is equal to 1, and we'll do check sat, and we'll look at the model that comes back. And when we run this, it's going to say, aha, winner could be 1 and hand could be 0. Because if 0 went into both sides, we would have 0 plus 4 minus 0, which is just 4, percent 3, which is 1, because percent means remainder. So we divide by 3 and look at the remainder, which is 1. Actually, it says there's an unknown function / constant percent, because it's not called percent. I think we might be right modulo. Is it modulo? No, it's called remainder. Sorry, gotta remember what it's called. Mod, there we go. It's just called mod. Mod, here we go. All right. Now, the thing though, is that right now, all we've done is we said that winner is equal to this and winner is equal to 1. Is it possible to find an answer for the hand? But that's not actually the question that we want. We want to know whether or not there could possibly be an error. So what we're going to do is we're actually going to assert the negation of this. Now, by asserting the negation of this, what we're doing is we're saying winner is this, and winner is not equal to 1. And now when we call check sat, we hope that the answer is false, that there is no solution. Because if there were a solution, then that would mean that there was an error in our program. So we'll run the program, and it's going to say unsat, which means that there's no solution to this. So that means it's right. Now, let's just suppose that we made an error in our program, where maybe what we'll do is we'll make it so that if it is ever the case, so this is ITE stands for if then else, if it's ever the case that the hand is equal to rock, which is 0, then let's just say that no matter what, Alice wins. So when the hand is 0, Alice wins, otherwise run the normal algorithm. Now, in this case, it is not the case that winner is always going to be equal to 1 when we just have an arbitrary hand, because if the hand that were chosen were rock, then the program has an error where it just makes it so that Alice wins. So now when we run this program, it's going to say, this equation is satisfiable. If the hand were 0, then winner would be 2 when it is supposed to be 1. So this right here is exactly what the reach compiler is doing. When you write this line in your reach program, for all you and hand, assert the winner hand equals draw, what it does is it translates this into a system of equations that corresponds to what your program does. Now, of course, it does this for the entire reach program, literally every single thing that you do. So if we were to go look at this version of tutorial 4, the program that gets generated, it's not, 13 lines. Instead, it's this program right here. So this program right here, starts at line 1 and it goes down to line 1098. And inside of here is the entire system of equations that correspond to everything that this particular reach program does. And if we look deep in the bowels right here, we can actually find this equation right here. It's actually this one right here, because this one right here says that we're asserting that variable 13 is equal to 1, and we're assigning that to variable 29, and we're going to assert that variable 29 is not true, and we want that to be unsatisfiable. And what's variable 13? Well, variable 13 is the result of calling the winner on a particular hand. So that's kind of just unveiling the covers, a little bit about how reach works. But what I'm trying to do by showing you this is to maybe demystify it at least a little bit. I mean, obviously, it's quite complex to think about how to take a program like this program and figure out what does this have to do with mathematical operations. But there are key principles that kind of make sense. So for example, when you compile your reach program, it's going to say that I'm going to verify for a generic connector. And what it means by this is that it's not going to make any assumptions about the kinds of values that are on the network, but you can configure it to do verification that is specific to each one of the connectors that reach supports. So like Ethereum, Algorand, Cosmos, Consensus, etc. And then when we say each mode, a good way to think about it is like Honest is essentially what Honest is doing is it's looking at each part of the program and assuming that it's run entirely by honest individuals, meaning that if your program contains a require statement, that is implied by all of the assumptions in your program. But when we say dishonest mode, essentially what this means is that we're going to assume that Alice is the only one that's honest. Or we're going to assume that Bob is the only one that's honest, and everyone else is dishonest, meaning that their values are completely unconstrained. So as an example, when we're verifying this program in honest mode, B is in control of the hand B variable. So what that means is that when we get down to looking at hand B, we're going to trust that it was actually done correctly. And so that's what honest mode is about. In contrast, when we go to dishonest Alice mode, that means that we're going to assume that Alice's code ran correctly, but we're going to assume that B's code was completely skipped. And he just picked a completely arbitrary hand B that had nothing to do with what we did. And we're going to make sure that the program is still correct, assuming that each individual participant is dishonest and honest. Now, when you are actually writing your reach program, you essentially can ignore all of these details. All you need to think about is what business logic you want to do. And then anytime there's something that you know about what your program should do, you can write that down as an assertion. So for instance, the winner function, if it gets, it is reflexive. If it gets the same argument on both sides, it returns a draw. And then we will derive the system of equations for your program. And there are certain properties that come for free in reach programs. So let's look at a little example. So imagine that that in this program, if A wins, I accidentally make it so that I'm going to return only one share of the wager rather than 2 shares of the wager. So basically what this means is that when I run this program, there's money left over in the account. And this is not okay on blockchain programs, because it means that you've lost money forever. When I compile this program, we're going to get an error. And this is the error right here. It says that on line 68, which is right here, the last line of the program, this exit, there's an assertion that says that this quantity right here, should be equal to 0. And what is that quantity? That quantity is the sum of everything that has gone into the program, so wager and wager, minus everything that's gone out of the program. So in this case, we're subtracting the share that goes to Alice and then the share that goes to Bob. Where in this case, the share that goes to Alice is equal to 1, 0. And the outcome of the game, V76, is equal to 2. And this part right here, this violation witness, this is what we showed before when I was showing you the details about how it works with the SMT solver. That is the set, that's what's called the model, the set of the solution to the system of equations. So what it says is that, Alice could have sent in 4 and Bob could have sent in 0, and that would have made it so that the results are bad. Now, one of the things that Reach needs to do is it needs to take your program, it needs to generate the SMT formalization, it needs to generate the additional theorems, what the balance is supposed to be and so on. It needs to track the balance inside of the logic throughout your whole program. It needs to create these variables, basically needs to create that other program, that SMT program, run it, and then interpret the output. So that's how we have, a connection that says, the thing that we called variable 35 really is the same thing as the result of calling getHand. And in fact, one of our engineers, Chris Nevers, he is just about to submit to finish a patch where it's no longer going to say V35. It's going to say hand A. It's going to keep track of what the actual original name was, which will make these errors even better, because they'll show you not only the source location information about where it came from, but they'll also show you the original name, which will be really convenient. In my experience, the main place that people find interacting with the formal verification engine in Reach to be kind of difficult is when we get to loop invariants. So if you look at the play and play again section of the guide, which is 2.7, one of the things that we do in that section is we expand the program to not only do one version of it, but to continue running the rock paper scissors game until after until there's no longer a draw. So this is the version of the program, and I encourage you to read the tutorial for more details. But one of the key things that happens is we have this part right here where we have the while loop, where we said this is a while loop that's going to loop until the variable outcome is no longer equal to draw. And this right here says invariant. Basically, what a loop invariant is it's something that is true before a loop starts, it's true after a loop ends, and it's true after the loop body ends. So one way to think about that is that when your programs, when you first get to the loop, this thing has to be true. And then that means at the start of the body of the loop, it's true. And the loop body can violate this invariant on the inside of the body. But when we get to the end of the body, it's got to be true again. And then that way, because it's true again, that means it's going to be true the next time we go in the loop, and the next time, and the next time, and the next time after that. And then when the program is over, when the while loop is over, it's still true because it was true on the last iteration. And so basically it's a way of abstracting the behavior of a loop by compressing all the infinite possible runs of that loop. Because when you have a while loop, it could run an arbitrary number of times. That means it could run 2 times, 0 times, 2,000 times, 2 million times, etc. And there's too much information if we were to analyze every possible one of those runs. So instead, we compress that information down into a loop invariant. And Reach requires you to insert that in directly. Other theorem proving strategies, what they would do is they would do something like they would expand out the loop into, they would basically inline the loop a certain number of times. So for instance, like 1,000 times. And then you would not be able to run the while loop more than 1,000 times, or else you would get beyond the bound that you checked. And the code name for this is bounded model checking. Generally, the way to think about what these loop invariants do is you think about what theorems come after the while loop, and whatever information you need to know afterwards has to be established by the inverse of the condition and the invariant. Generally, the most important thing to put in your invariant is what the balance of the program is, where you need to know about whether or not anything comes in or out. So in this case, the balance in the rock, paper, scissors program never changes throughout the course of the while loop, because the 2 players paid at the beginning. So therefore, we just know that it's always going to be 2 times the wager. But if you think about something else, like an example would be, I don't know, like imagine that you were doing like an automated market maker where individuals had accounts, like liquidity accounts. And each one of those, we would keep track of how many tokens of various types they deposited. And there would be like a little ledger. So what we would need to know then is that the balance of one of those tokens is essentially a sum of everything inside of the ledger. And then the goal of the while loop is that if it modified that ledger, it would have to guarantee that it modified it in concert with modifying the actual balances of the tokens. One question that people often have is how efficient is the SMT solver? We talked about how, when you're doing something like this example, you might think that what happens is you're going to enumerate all 2 to the 256 different possibilities for how, for what hand could be, and that would be really inefficient. And that would be really inefficient, but that's not what the SMT solver does. Generally, SMT solvers like Z3 that we use are designed for programs that are millions upon millions of equations big. And even large reach programs tend to only be on the order of a couple thousand lines when converted into the SMT model. Like the actual reach program, the biggest ones that we've written so far have been like 250 lines. And we've written some complicated programs. So I can't make any promises, but I find it unlikely that we're going to get into a situation where there's going to be bad performance out of the SMT solver because of the program that people wrote. In contrast, if your program takes a long time to verify, that probably means that we, the reach compiler, are not doing the best job converting it into the right kind of theorem. And then you should consider that an error. And when I say slow, essentially anything that's not instantaneous is slow. The Z3 should return basically immediately. I think the longest program that takes to compile that we have is the tic-tac-toe example. And that's because it has, I think it has like 800 theorems. And so this right here is slow. So see how it took it was like you noticed how long it took for doing the honest version. That is like worst case times. Now, there's something that's kind of related to performance, which is the precision of the theorem prover. And there's a feature that we have that Reach has. So if you look at constructing applications, there's this set of options that you can give. And one of the options is called verify overflow. Although I think we're going to change it to verify arithmetic. And basically what this does is it makes it so that when verify overflow is true, which is not the default, then we're going to check statically that no operations in your program could possibly do an overflow. No matter what, when we compile your program, it's going to check this. But when this is on, it's going to make sure that there are assumes inside of your program that will check that. So as an example, like take this program right here, the 6th version of the tutorial. Where would this actually be relevant? Well, right here, notice that we do 2 times the wager. And we do 2 times the wager down here. Well, that essentially means that the wager cannot be more than 2 to the 128 ETH. Way, 2 to the 128 way. Because if it were 2 to the 128 way, then multiplying it by 2 would get a number that would be too big, right? Basically, it's like if your number was 255 bits, then if you multiplied it by, if your number was already 256 bits, then multiplying by 2 would get you a 257-bit number, and then that would be illegal. So if we turned verify overflow on, we would have to go back to this part of the program right here, and we would have to add in something where we'd say we have to assume that the wager is less than 2 to the 255 plus 1. And if it isn't, then that means that our program is wrong. And of course, we're going to have to do a require right here to make sure that that's true. And other than that, I don't think there are any places where this particular program would be a problem. But programs that do more mathematical operations tend to have more things there. And adding this basically increases the number of things that Reach will verify. And the reason that this is off by default is because it's very painful to make sure that all these things are there. You should do that, but you shouldn't be super worried about this because, like the standard practice in the Ethereum world and so on is to delay these checks anyways. And the thing is that we're doing this checking at runtime anyways. There's kind of a theoretical reason why you want this on, which is basically that you want to make sure that it's possible to reach the end of your program. But I don't know, this is kind of I'd rather not spend a lot of time talking about this. It's kind of a deep idea, but this verify overflow thing is useful. One of the things that you find with Theorem Perverse is that because the Theorem Perver that we use is entirely automated, the performance can be unpredictable in general, you know what I mean? But for the kinds of programs that you write in Reach and that the Reach compiler produces, I don't think that we get in the bad domains of Z3. I mean, like I said, it's really designed for analyzing things much, much more complicated than simple dApps. One question that people often have is, what should I even verify? And this is kind of a hard thing to say, because the thing that you can verify are things about the variables in your program. So you want to think about, what behavior do you not want your program to exhibit? Here's an example of that. In this program, this being the rock, paper, scissors program, we know that in our domain, the winner function, when you give it two hands that are the same, you should always get a draw. So that's a property that we know about this function winner. But what are properties that are useful that are like inside of the program? Like, is there anything meaningful that we can say about, the relationship between hand A and hand B and the final outcome? I mean, in this program, there's not really anything like that. Probably the only thing is that, when we cryptographically commit, when Alice cryptographically commits to her hand, we want that to be the same thing later on. And that's what this check commitment thing does. But imagine we had a version of this rock, paper, scissors program that worked a little bit differently. So here's the way that would work. Notice that inside of the while loop, A publishes something, then B publishes something, then A publishes something again. And before this, A publishes something and then B, and then we're done. So what this means is that we could keep track. If we were to keep track of how many times everyone does something, then if the game took n rounds, Alice would do 2 times n plus 1 actions, and Bob would do n plus 1 actions. So essentially, Alice would be doing twice as much stuff as Bob. So what we could do is we could add a new variable to our program. We could add in the number of rounds and then the A steps, and we'll call it steps A and steps B. And then we'll say that the round starts off at 0. There's one Alice step and one Bob step. And then what we could do is down here, when we are ready to go to the next round, we would say that, there's now been the number of rounds that there were before plus 1, and that then Alice has taken steps A plus 2, and Bob has taken steps B plus 1. So essentially what I've done is I've added something to my program to account for information that I know about. And now that this information is there, I can try to state a theorem about what I expect that value to be. So I can write, I'm going to assert that steps A is equal to the number of rounds times 2 plus 1. And I'm going to assert that the number of steps that B took is equal to the number of rounds times 1 plus 1. Now, if I try to run this program and check it, it is going to fail. And it's going to fail because the loop invariant is not precise enough. Okay, so first of all, I just have little tiny mistakes. So I have to write rounds, steps A, and steps B. Okay. Live programming. Okay, so notice that that the assertion fails. And the reason it fails, because it doesn't say this, but I know that the reason it's failing is because there's no information in the loop invariant about the connection between these loop variables and their values. But what I can do is I can add into the loop invariant more information. So I already have that the balance is 2 times the wager, and I have that the outcome is an outcome. But what I can do is I can add the additional constraint that steps A is equal to rounds times 2 plus 1, and steps B is equal to rounds times 1 plus 1. Now, you may think this is pointless because I've just verified, I'm just adding to the loop invariant things that I knew before. But actually, in this case, it's true, because it's true beforehand when the rounds is equal to 0, and it's going to be true after. So what I'm really doing is I'm checking to make sure that this modification is valid. So now I go and I try to compile my program again, and it should succeed. I haven't tested this, but it should succeed. All right, there we go. So it succeeds. So now, why is this useful? Well, what I've done is I've taken a desire about something, about expressing something about what this program is supposed to do. I've encoded it as variables in my program, and then I've added a verification about that. Now, why is this useful? Well, now I can look at this and I can say, it stinks that this theorem is true. This theorem is a bad theorem to be true because it clearly shows that this program is unfair to Alice. It's unfair to Alice because she has to do twice as much work as Bob does. And we know on networks like Ethereum, that means that she is paying twice as much gas as Bob is. So it would be better to rewrite this program so that, for instance, I could prove a theorem that said something like the number of steps that A takes is equal to the number of steps that B takes plus 1, or the number of steps that B takes is equal to the number of steps that A takes. So what I would like is I would like this theorem to be true, that steps A is equal to either steps B plus 1, or it's equal to steps A. And if I tried to write this, now if I tried to prove this theorem, it's going to be false. And it's false because that's just not the case with what we have right before. So see, it's going to say that, well, actually, the number of things that Alice does could be 5, and the number of things that Bob does could be 3, and so that doesn't satisfy this equation. And so then what I could do is I could take this goal of trying to make it more fair and then re-engineer my program. The way that I would re-engineer this, by the way, is I would make it so that on even rounds, Alice goes first, and on odd rounds, Bob goes first. And then that way they're going to balance one another out because basically they'll take turns adding 2 to either side. And so that's the sort of thing that you do when you start. You start from a program that has the correct behavior. And there's it works, but it's not the best program because there's some extra thing that you want it to do. There's some thing that you would like to prove that it does. And when you make it so that you can have Reach prove that thing, you find that it's false. And so then Reach guides you to re-engineering it to try to satisfy that equation. So that's the most effective way to use the Reach verification engine, because what you want to do is you want to take things that are about your domain and embed them into your program via variables, and then you can prove things about them. And of course, I've done this with the dumb example of the rock, paper, scissors program. But the point is that even that program has complex behavior and complex theorems that you could try to prove about it. And the fact that a simple program has these properties and they're subtle tells you that more complicated programs have much more complicated properties. And that's why it's so important to do formal verification of dApps so that you can have safety.
1, 2, 3.